Today we're going to be talking about memory, and we can actually talk about the idea of learning and memory separately. Learning being the process of acquiring new information, and in some way, when you learn something and you're in school, you learn a new fact, you learn how to do some new kind of math. In some way, that must be changing your nervous system. It's either changing the synapses or the neurons or the neurotransmitters. Something's changing in our nervous system to allow us to learn information. And memory is the ability to store information and then retrieve it when we need. So memory is the storage, and where and how do we store information in the brain? So we'll start with the most basic type of learning, and the most basic study of learning is on this marine slug called an aplysia. There's been lots of studies of learning in the aplysia because it has very few and they're very large neurons. So you're able to see pretty easily the neurons and the connections. And the neurons are also identical between different aplysia. And so here we have this aplysia where it has a siphon out here extended, and then this gill spread out, basically. And aplysias make what we call a withdrawal response, that if the siphon or the mantle or the gill is touched, it withdraws into itself, right? You've probably seen different marine invertebrates, maybe at the beach in tide pools, and when you touch them, they withdraw. And so scientists have been able to map this neural path from a touch receptor to what we call an interneuron to a motor neuron. Okay, and that's the withdrawal response. Now, in terms of learning, we have two types we're going to talk about. The first is the idea of habituation. And habituation is the idea that if something happens over and over and over again, there's a decrease in response to that stimulus that's presented repeatedly. So this happens to us as well. Let's say you're studying, I don't know, in some coffee shop, and when you first get there, you hear the sound of the coffee maker or the espresso maker, and you're studying, and then you kind of look up, what was that noise? Okay, you see what it was, keep studying, then you hear that noise again, someone's making a latte, that sounds so good, and then you look up, you hear the noise, and then you kind of focus back on your work again, and after a period of time, you stop responding to that noise. It's almost as if you don't hear it anymore. We say you habituate. You stop sending as many signals, your brain stops sending as many signals that makes you kind of aware of that noise. So decrease in response to a stimulus that is presented repeatedly is the idea of habituation. And we see habituation in an aplysia, that the first time you stimulate or you touch the gill, it withdraws the gill. But if you repeatedly stimulate the gills, meaning you keep touching those gills, the aplysia eventually stops withdrawing. And so they've done research to show that that is not a function of muscle fatigue. It's not as though the aplysia gets too tired and its muscles can no longer withdraw anymore. We see that direct stimulation of the motor neuron produces a full-size muscle response. So here we have the siphon. Here's our sensory neuron. And then it synapses on the motor neuron that would make the gill withdraw. So here's kind of our schematic of the aplysia. This is very simple marine invertebrate, that a stimulus, something would touch this siphon that stimulates this motor, the sensory neuron, and then the sensory neuron synapses. Here you can see are the synapses, the presynaptic terminals. There's the neurotransmitter that is then synapsing on the motor neuron, which would cause the gill to withdraw. And you can see that they've done research to show that after repeated stimulation of this siphon, you don't get as much of a gill withdrawal. And so when they say it's not muscle fatigue, if they electronically basically stimulate the motor neuron, you get a full-size gill withdrawal, meaning it's not that there's some kind of muscle fatigue or motor neuron problem. That motor neuron is still working just fine. And it's not a change in the firing of the sensory neuron, meaning if you actively or electrically stimulate the sensory neuron, you still get a full-size response. What happens is we see a change in the synapse between the sensory and motor neurons. You actually see less neurotransmitter being released between the sensory neuron and the motor neuron after repeated stimulation, after repeated stimulating the siphon, touching, and then eventually what happens, you can see here, is there's actually retraction of some of the synaptic terminals, and you get less neurotransmitter release, and so you get no response. The motor neuron basically isn't stimulated anymore. There's not enough neurotransmitter to cause a postsynaptic potential that will reach the threshold, and so you get no response. So what we see is over time, this aplesia learns. We would call this very basic learning, and this is how we see learning actually represented neuronally, in that it learns that, hey, this is just going on and on, there's no need to keep responding, and these actual synapses retract and we get less neurotransmitter released and therefore no response. We can also use the aplesia to look at another type of learning called sensitization. Sensitization is that after a very intense stimulus, an organism becomes overly responsive to mild stimuli. So again, for us, we experience sensitization as well. If you are studying quietly in the library and then you hear a really loud crash, I don't know, something falls off a bookshelf, and you jump, that's an intense stimulus, you kind of become overly responsive to mild stimuli after that, meaning that next time somebody kind of walks by you or makes a little noise, you might jump a little bit more because you have been sensitized. You've had this extreme stimulation, extreme stimulus that then makes you kind of hyper responsive to mild stimuli. And what we see in aplesia, if they do an electrical shock to the tail, that's a very strong stimulus in the sensory neuron. And there are, in some cases, some interneurons, but basically what we find is after that tail is shocked, you end up with an increase in neurotransmitter release to the motor neuron. And so we know that behavioral change or learning in an aplesia can be based on increases or decreases of activity in the synapses. So how can we represent the simplest form of learning is really a change in the way these synapses function, which is pretty amazing in something as simple as an aplesia and a way for us to kind of represent learning. Now, what about in humans? We're going to talk about the hippocampus. This is a very important brain area when it comes to memory. And there's a researcher, Donald Hebb, who proposed that when two neurons are repeatedly activated together, their connection will become stronger. And we call that a Hebbian synapse. And that maybe these types of synapses, two neurons that are repeatedly activated together, could be a way that we store memories in our brain. And the idea here is that cells that fire together start to wire together. So memory in a simple hippocampal circuit or LTP, long-term potentiation. Again, this is kind of the simplest. We're now looking at the cellular form of learning or memory. That if we place electrodes at a presynaptic cell and a postsynaptic cell in the part of our brain that we think is responsible for memory called the hippocampus, typically you stimulate the presynaptic neuron and you get a release of the neurotransmitter glutamate. And glutamate causes a postsynaptic potential, just like we've talked about in this class before. But if the neuron is bombarded with a series of stimuli, rapid stimuli again and again and again, a tetanus, as we see here. So if we bombard that presynaptic cell with a lot of rapid stimulation, the postsynaptic cell changes and produces, you can see here, much stronger postsynaptic potentials, much stronger excitatory postsynaptic potentials. So here here's the postsynaptic potential when the presynaptic cell is just firing at kind of a slow average rate. And then if we give a very strong series of stimulation to that postsynaptic cell, all of a sudden we get what we call potentiation. We get a stronger excitatory postsynaptic potential from that postsynaptic cell. And so this postsynaptic cell, we would say, actually learns. And this increased excitatory postsynaptic potential that you see here is long-lasting and stable, which means it stays that way. The cell has a learning or a memory of this rapid stimulation, and so it stays this way, and we call this long-term potentiation. We have this increase in the excitatory postsynaptic potential that stays with that cell long-term. And long-term potentiation occurs at pathways in the hippocampal formation, part of the hippocampus, and the dentate gyrus, as well as other brain areas. The most studied forms of LTP, when they're looking at which cells can actually show this long-term potentiation, are cells and synapses that use the transmitter glutamate, and depends on two different type of receptors, NMDA receptors and AMPA receptors. And you'll see when we go to the next page, during normal activity, glutamate released at these synapses only activates your AMPA receptors. Oh, let's see here. So in a typical situation where you have a presynaptic cell in the hippocampus that is sending a message and sends glutamate to the postsynaptic cell, glutamate attaches to only AMPA receptors. I'm going to look here. I think I have this video here, or this slide. So here is the axon terminal from our presynaptic cell. There's glutamate as our neurotransmitter. And the postsynaptic cell has both what we call AMPA receptors and NMDA receptors. And typically, the NMDA receptor is blocked, and you can see here, is blocked by magnesium. And so when glutamate is released from the presynaptic cell, it only goes through and activates the AMPA receptor channels because the NMDA receptors are blocked by magnesium. But with repeated activation of the AMPA receptors, so with that strong series of stimulation, of the AMPA receptors, that depolarizes this neuron. We've got glutamate being released from the presynaptic cell, and we are depolarizing the postsynaptic neuron, And this very strong repeated activation actually drives the magnesium out of the NMDA channel and allows calcium ions to come in. So glutamate is still going here into the AMPA channels. The magnesium is dislodged from the NMDA channel, and calcium ions come in. Beyond that, we also have retrograde neurotransmitters that are probably gas neurotransmitters like nitric oxide that come from the postsynaptic potential and kind of reinforce the neurotransmitter release from the presynaptic cell. And what happens is by having this change, having the magnesium come out of the NMDA receptor, calcium go in to the NMDA receptor, these changes make the synapse more responsive and enhance the postsynaptic potential we get here. The postsynaptic cell now has, you can see, a stronger response as more neurotransmitter is released and more AMPA receptors are actually activated. So again, this is a very simple, I won't say simple, but at a cellular level, we can see learning, we can see long-lasting change in two cells that are firing together, and then we get a permanent change, we get this permanent elevated response in the postsynaptic cell that looks like memory, that looks like this cell remembers, oh, I've been activated a lot before, I'm going to just increase my response. So that is at a cellular level in aplesia, how we can look at learning with habituation and sensitization. And that's how at a cellular level in the hippocampus, we can see long-lasting changes that look a lot like memory. And we know the hippocampus is where memories seem to be consolidated or changed from short-term to long-term memory, which we're going to talk about right now. And so we can kind of see cells in that part of the brain that seem to look as if they remember. So now let's look a little bit bigger picture instead of at the cellular level. Let's talk about learning and memory in a bigger picture. That in terms of when we remember information, there seems to be three processes that are going on. The first thing that has to happen is you have to encode some kind of sensory information. And so you either see something that you remember, or hear something, or smell something, or touch something. You have a sensory experience that goes into what we call our sensory buffers or iconic memory, in that you just bring that information into your brain, into your central nervous system. And that information can then be encoded into what we call short-term memory. Okay, so information is brought in from our sensory, from our senses. It's stored for a very, very short time in our just iconic or sensory buffers, and then is encoded into short-term memory. Now, short-term memory, which we'll talk about, is exactly what it sounds like. It's short-term. Most of the things in our short-term memory, we start to forget within a few seconds. Short-term memory is limited in how much information we can store in our short-term memory. There's a magic number of 7 plus or minus 2 bits of information. So you can store a limited information, a bit of information in your short-term memory, about 7 pieces of information. So 7 words, if you're thinking of a list to remember of, I don't know, grocery shopping, or a phone number has 7 numbers, so you have a chance to remember them all. And if that information in your short-term memory is practiced, is repeated, if you keep thinking about it, then you can potentially, what we call, consolidate what's in your short-term memory into your long-term memory. So information that you think about, that you study, that you repeat over and over again can go from short-term memory into your long-term memory. If you don't repeat any of the information, if I just told you a list of 7 words, you didn't think about them again, and then I asked you about them in an hour, you wouldn't remember them. That information just is not stored. And so consolidation is the process of changing short-term memories into long-term memories. This is actually the part of the memory process that we think the hippocampus is important for. And then we have retrieval, which is where information that is stored in long-term memory can be brought back. That you learned something many years ago and you retrieve that memory through this process of retrieval. So how does memory work? Memory storage requires actual physical changes in the brain, and we do see changes. They've done studies of the brains of rats that were housed in a standard condition, regular kind of rat cage, an impoverished condition. This is a very, very boring, empty rat cage, and an enriched environment, as you can see. Wow, it's like a rat palace. It's so exciting, so many things to do. And so, oops, sorry. Certainly the rats that live in this enriched condition are learning more. They're learning how to climb up this ladder, or balance on this bar here, whatever it is they're learning. And so they're having a much more learning and memory happening than the rats who are in impoverished condition, just sitting there kind of doing nothing. And they find that animals that were housed in these enriched conditions had actual changes to their brain. You could see that they had heavier, thicker cortex of their brain, so that outer covering. They had enhanced activity at the cholinergic neurons. Their dendrites, or their neurons had more dendrites. There was more branching, so more connections, more synapses. There were larger synapses. They had actually more neurons in the hippocampus, and they had enhanced recovery from brain damage. They were able to recover more when they were was given experimental brain damage. So you can actually see changes in the brain due to learning and memory. All right, let's think about long-term memory. We're going to break it into 2 areas, and you'll see with memory there's a lot of different terms. Declarative memory, long-term memory, are things that you know that you can tell others, things that you can declare. So you can talk about what was, the first president of who was the first president of the United States, um, different sorts of things you can talk about. And we also have in long-term memory what we call non-declarative or procedural memories. And these are memories of things you can do, that you can do, and that you show your memory by doing these things, like riding a bike. I can't really tell you how I can ride a bike, but I've learned how to ride a bike, and when I get back on it, my body just knows how to balance and how to do everything it needs to do to ride the bike. So non-declarative or procedural memory, these are things that you know how to do, can't really explain them or talk about them. And declarative, those are memories that you actually can talk about, things, facts, and memories like that. We're going to talk right now about non-declarative memory for a second. So different forms of non-declarative memory involve different brain regions. And we're going to talk about associative learning as a type of non-declarative memory. Again, a memory that you couldn't really talk about, but that happens. And this is when you have an association between 2 stimuli. and you get basically a stimulus and a response. This is classical conditioning. You might have learned in your Psych 101 class about classical conditioning or Pavlovian conditioning, where a neutral stimulus repeatedly paired with a stimulus that elicits a response begins to elicit the response from the stimulus when presented alone. So what is happening in classical conditioning? And this is the very famous Pavlov experiment, where you have what we call an unconditioned stimulus. An unconditioned stimulus in this case is food. Food is a stimulus that elicits a response. The response in a dog is salivation. If you show a dog food, they will salivate. And we call this unconditioned. Conditioned is another word for learned. It's an unlearned stimulus. You don't have to teach a dog to salivate to food. It's automatic. The dog will automatically salivate to food. And the salivation to food is what we call an unconditioned or unlearned response. Again, you don't have to teach the dog, when I show you food, you should salivate. It's an automatic or unconditioned response. So we have the unconditioned stimulus of food that automatically elicits an unconditioned response, which is the salivation. Now, the learning process, or the conditioning learning process, is when we're going to teach the dog to give an unimportant stimulus the properties of an important one. We're going to have this association between two stimulus. So we have this unconditioned stimulus response, unconditioned stimulus of food leading to an unconditioned response of salivation. There is also, here we have a neutral stimulus. In this case, our neutral stimulus is a bell. When you ring a bell, there is no salivation from the dog. A bell is pretty neutral. Dog doesn't really have any particular response to the sound of a bell. Now, during our conditioning trials or our learning trials, you ring a bell at the same time you present the food, and the dog starts to salivate, mostly because he sees the food. And so you repeatedly pair the bell and the food together, and then you get the salivation. And again, bell and food, and you get salivation. Bell and food, and you get salivation. And so during the conditioning, you get the bell and the food and the salivation. After a certain amount of time, all you have to do is ring the bell and the dog will salivate. And the terms here now, the bell has gone from being what we called a neutral stimulus over here, didn't have any meaning to the dog, to a conditioned stimulus, a learned stimulus. The dog has learned that when I hear a bell, I'm going to get food. So the bell then, after the conditioning trials, becomes the conditioned stimulus. And the salivation, and this is key, salivation in response to hearing a bell is called the conditioned or learned response, because typically dogs don't salivate in response to a bell. Notice that we have the same response, right? It's the salivation of the dog is an unconditioned response when it's in response to food. It's an unlearned response when it's in response to food. But salivation becomes a conditioned or a learned response when it is in response to hearing a bell. That's the learning. The dog has learned that the bell leads to must mean food, and the dog starts to salivate. In that case, the dog has been classically conditioned to salivate in response to the bell. Now, this type of non-declarative memory, the dog wouldn't be able to tell you what's going on. Well, dogs can't talk. But even in people, we talk about maybe anxieties being and fears perhaps being classically conditioned, that we can't really explain why it happens or why we have this emotional response. but nonetheless, we feel it. And it seems that the cerebellum is a brain area that's important for classical conditioning. Okay, we have different areas of the brain important for different parts and different types of memory and learning. Another type of non-declarative memory is called instrumental or operant conditioning. And this is when an association is made between a behavior and the consequence. So operant or instrumental conditioning has to do with consequences. This is how we train our dogs. If anybody has children, very often it's how we train children how to do things, is we give reinforcements. Hopefully we give rewards. And if a response is followed response is followed by either a reinforcement or punishment. So reinforcement is an event that increases the probability of a response. Again, hopefully I do this with my children all the time. If you want to see something happen, again, a particular behavior, you reinforce it. So it might be a sticker, it might be a M&M when they were little. Oh, you did something great. You were so nice to your sister. You cleaned up your room. Here's a sticker. Here's some kind of reinforcement. And children start to learn, oh, if I do this, I'll get some kind of reward. And eventually they start to do that behavior more and more. Dog training, animal training is very much using these principles. And punishment, that's an event that suppresses the frequency of an event. That's a punishment would be something that's that's a negative consequence, right? And if a behavior is followed by a negative consequence, the animal or the child starts to learn, hey, I shouldn't do that because I'm getting a punishment. Something is not positive. A lot of this research on reinforcement started with Skinner and the idea of a Skinner box where they have a mouse with a lever, and he learns that in this case, if you push the lever, food comes out. Push the lever, food comes out, and eventually the mouse learns, hey, learns to push the lever because that's leads to a very positive response. But if you want to teach a mouse, hey, don't touch this lever, then perhaps every time he touches the lever, the mouse gets a shock. That would be a punishment. And eventually you teach the mouse not to touch the lever. So this is when organisms adjust their behavior based on consequences. The brain areas for instrumental or operant conditioning are unknown. Perhaps the nucleus accumbens is involved when we're talking about reward. That seems to be the reward area of the brain. And again, we'll talk more about that when we talk about drug use. But this is another type of non-declarative memory where these are associations that happen over time. Another type of memory would be remembering place or spatial locations. And it seems that in the hippocampus, we have what we call place cells that become active when an animal or person is moving toward a particular location. So there are actually cells in the hippocampus that seem to remember place or space. Pretty cool. Let's see, going back to learning and memory, we talked about this, the sensory buffer. That's the briefest recollection of all your sensory impressions. That information goes into short-term memory, which usually lasts about 30 seconds or longer if there's rehearsal. And then long-term memory can last days, weeks, months, or even years. Long-term memory has a vast capacity, but is subject to forgetting over time. And what happens is this memory trace does not deteriorate over time, but it's interfered with by events that occur before or after. And so it becomes harder to retrieve the information. We believe the information is there, but it becomes harder to retrieve it. So some memories become unstable or just difficult to retrieve. And then reconsolidation is the return of a memory to stable long-term storage after you've recalled it. People who have problems with memory, we call amnesia. That's a very severe memory impairment. And we can break amnesia either into global amnesia, which would be forgetting past and future events. More typically, we see a particular pattern. Retrograde amnesia means loss of memories formed before the onset of amnesia. So if here is now some kind of head injury or accident or something happens, if someone has retrograde amnesia, they forget all the past events, anything that happened before the onset of their amnesia. And then anterograde amnesia is inability to form memories after the onset of a disorder. So something happens now and people have trouble creating new memories. That's anterograde amnesia. And global amnesia, like I said, would encompass both retrograde and anterograde. So studies on amnesia have helped to clarify distinctions between different kinds of memories and their mechanisms. And again, we've talked about this hippocampus area right here in the temporal lobe that seems to be really important for consolidating memories. Hippocampus is supposed to look like a seahorse, which is why they have this picture here. So long-term memory, we've talked about non-declarative, things you can show. We talked about classical conditioning being part of this, seem to be controlled by the cerebellum. We're also going to talk about skill learning, like knowing how to do something, riding a bicycle, basal ganglia and motor cortex. And then we also have declarative memory. These are things that you can tell other people. We think these are really hippocampal dependent. So the hippocampus is really important for declarative memories. And we can break declarative memories into two different kind of aspects. Episodic memory. Episodic is remembering episodes, remembering things that have happened, like your first day of school, what you wore to your prom, those sorts of things. We think that those episodic memories are stored in the cortex, again, and dependent on consolidation going into long-term memory with the hippocampus, or due to the hippocampus. And then semantic long-term memories, that's knowing things, knowing the capital of France, knowing who, again, the first president of the United States was, knowing information. And again, that seems to be hippocampal dependent and stored in the cortex. One patient we learned a lot about in terms of memory is patient HM. Who had bilateral removal, he had a surgery of his medial temporal lobes, which included his hippocampus. So he had seizures that caused intractable seizures that they needed to remove. Bilaterally means both sides of his temporal lobe, and both of his hippocampi were removed. What they didn't know at that point is how important the hippocampus was for memory. And what we found is that this patient had massive anterograde amnesia after the surgery, meaning the loss of ability to form any new memories after the surgery. He couldn't remember events after the operation. So again, if we look back here to anterograde amnesia, patient HM couldn't make any new memories, basically, after the surgery. He couldn't learn his way to find the bathroom in the hospital. He couldn't remember telling a story a few minutes later. A doctor would come in and say hello, introduce themselves, leave, come back in, and the patient would not remember ever having met that doctor. Had no way to consolidate or to change any short-term memories into long-term memories. Also had moderate retrograde amnesia, meaning he lost memory for about 1 to 3 years before the operation. But the most significant problem with patient HM was without having either his right or left hippocampus not being able to create any new memories and having anterograde amnesia. When we look more detailed, he had a very clear declarative memory deficit, meaning he couldn't state his memory in words. He couldn't say anything, couldn't learn any new facts or information that could be answered using what questions. If he taught him a new joke and asked him the joke, he wouldn't be able to remember it. All of that declarative memory was a very clear amnesia. But what's real interesting is that his procedural memory remained intact, meaning he could create new procedural memories. He could develop new motor skills. And these are those how memories. And they did things like reading words written backwards, like here. That is a skill. And if you practice this over and over, you get better and you can read these backwards words quicker and quicker. And what they found is they would teach patient HM over and over how to do this. He would never remember that someone had been in teaching him this before. He would never remember having done it before. If you asked him, hey, have you ever read words backwards? He would say no. But he would get better and better and better at doing this. Same with drawing something seen in a mirror. This is another procedural memory task. If you've ever tried to draw something while looking in the mirror or try to do something, you can know how hard that is. And again, they would teach him over and over and over again how to do this mirror drawing. And you can see that over time, he would get better and better. So he was learning, he was able to form these new procedural memories, but had no declarative memory of it. He would say, I've never done this before. I've never seen this before. But yet you could tell by testing he was getting better and better. And we see that surgical patients who had a similar surgery, but their hippocampus was not damaged, had no memory impairment. So it lets us know that the hippocampus is important for consolidating new memories, for leading to anterograde amnesia, and particularly with declarative memory. Procedural memory we don't think is dependent on the hippocampus. You can see a similar situation with monkeys. We can do a non-matching to sample test where the monkey is shown a sample object. And when he displaces it, he gets a pellet of food beneath it. Okay, there's a key. Good job. And then after a delay, the monkey is presented with the original object and another object. And the monkey has to then pick up the object that he was not shown at first. And so even though he can't speak, in a way he's declaring that he remembers the key because he knows he's got to pick up the other object. So this is a way to test declarative memory in an animal that can't actually speak. And what we find again is medial temporal lobe damage, similar to HM, causes impairment on this declarative memory task. Patient NA had amnesia due to damage to the dorsomedial thalamus and mammillary bodies. Like HM, he has short-term memory, but can't form declarative long-term memories. And so they had a very similar symptom profile, but paired with damage to different regions. And this suggests that there's a larger memory network, that it's not just as simple as information goes through the hippocampus and that then becomes long-term memory, but the dorsomedial thalamus and the mammillary bodies are also probably part of this circuit or network that helps us consolidate short-term to long-term memories. And now just a couple of diseases that affect memory. The first is Korsakoff syndrome. This is a degenerative disease of memory caused by damage to those mammillary bodies. Again, here they are. Dorsomedial thalamus and frontal cortex. This is a disease that is often presented in people who have had long-term, very severe chronic alcoholism. We're talking about very, very long-term, 20, 30 years, extremely high alcohol intake. And what we see is that brain damage starts to be caused by a long-term thiamine or B1 deficiency. That seems to be what causes Korsakoff's, that the body has problem absorbing thiamine, and it's this deficiency that causes damage to the brain. Oops, sorry. They start to not be able to metabolize glucose, leads to the shrinkage of neurons throughout the brain, particularly in the mammillary bodies and hippocampus. People get apathy, confused, amnesia, and very severe amnesia. In fact, they probably lose about 20 years of their memory. Retrograde. So if they start to have symptoms of Korsakoff's where they have memory problems, typically they're in their 50s or 60s, they've had long-term alcohol abuse, and they lose 20 years or 30 years, they think they're 20 years old again. And then you might even hold up a mirror in front of them and show them a 60-year-old person, and they'll say, what kind of trick are you pulling? This can't possibly be me. I'm 20 years old. Who is this person with gray hair and wrinkles? So they have a very significant memory problem. And they also do what's called confabulating, and that is when you ask a question, when someone confabulates with who has amnesia, they give you an answer. It's very detailed, but it's totally wrong. It's like a guess, but they believe it. It's not necessarily like they're lying to you, but you just ask them, oh, tell me what you did for your birthday last year. And they'll give you a long, detailed story that is absolutely not true. And that would be confabulation. Dementia, this is another failure of cognitive ability, and this happens in a more natural ways as people get older, including memory failure and disorientation. Alzheimer's disease is a form of dementia, and this is when the brain starts to show cortical atrophy and reduced metabolism. Alzheimer's disease starts as memory loss of recent events, and then the memory impairment becomes very extensive, so that they can't remember almost anything. It's hard to have a conversation. Context, prior information, everything seems to be lost. And there's other cognitive impairments as well, but the memory impairment is severe. What causes Alzheimer's disease? We see changes, cellular changes in the brain. We see in the brains of patients with Alzheimer's disease plaques and tangles. Amyloid plaques formed by this beta amyloid buildup in the brain, and you can see these plaques here. And tangles, those are just, again, abnormal cells that can be distinguished particularly on autopsy. And you see a loss of neurons that make acetylcholine in the basal forebrain. So there are definite brain changes that we see in Alzheimer's disease. The diagnosis is typically only made post-mortem, meaning we can only confirm those plaques and tangles typically on a post-mortem analysis. When the patient is alive, we can do testing, psychological, neuropsychological testing that can suggest Alzheimer's disease, but we can't make a confirmative diagnosis. We could also now look at PET scanning, injecting a dye that attaches to these beta amyloid beta amyloid and is detected by a PET scan. And you can see here that these are higher concentrations of the dye that has an affinity or that binds to beta amyloid. And in Alzheimer's disease, there's a lot of binding. You can see that this patient has a lot of beta amyloid in their brain. Here's cognitive impairment. Still a lot, but less, right? High would be red, and then the low is the blues and purples. And in control, you can see there's very little. How can we help or postpone Alzheimer's disease? Physical and mental activity might postpone Alzheimer's disease. So mental activities, using your brain, physical activity, getting exercise, that seems to be correlated with people doing better, having later onsets of dementia. So very important to keep exercising and using your brain and your body as you get older. Thank you very much.